Welcome to Stories from the NNI. I'm Lisa Friedersdorf, Director of the National Nanotechnology Coordination Office. Today, it's my pleasure to welcome Adam Rondinoni, Co-Director of the Center for Integrated Nanotechnologies, or CINT, at Los Alamos National Laboratory. Adam, thank you so much for joining us today. Can you get us started by telling us how you first got involved in nanotechnology?
Sure. Well, let me just say thanks for having me. I'm super excited to be here. So, my story with nanoscience starts, I guess, back around 1997. I actually went to Appalachian State as undergraduate in chemistry, and I studied environmental chemistry. And I wanted to go to Georgia Tech, and they had a pretty good program, folks studying environmental chemistry. And so I thought I would go there and do that. And I've always been a little bit of an environmentalist, and maybe that'll be important later. Instead of pursuing environmental chemistry for my PhD, I went into material science and studied magnetic nanoparticles, used some of my synthetic expertise to make particles and analytical expertise to study how the magnetic structure functioned and how to control magnetic behavior. It was a lot of fun. And so I came out of Georgia Tech after about 4 years. And it just so happened that during my time at Georgia Tech, I had been traveling to Oak Ridge on a regular basis to do neutron scattering at the high flux isotope reactor. And we were using neutrons, of course, which are sensitive to magnetic moment, to understand the magnetic crystal structure of the nanoparticles and their time-dependent behavior. And so when it came time for me to leave Georgia Tech, Oak Ridge extended me an offer to go be a Wigner Fellow, which is a named fellowship, and I took that, and I was pretty excited to go. And then since that time, I've basically worked in nanoscience of one flavor or another. I sort of moved on from synthesis to more of the electrochemistry. There's a bit of a story behind that. It kind of goes back to my environmentalist roots, and also goes back to the time I spent working in Senator Alexander's office on energy policy, when I really got to see, wow, we're up against some big problems here and the public expects solutions. And so I took some time off from 2008 to 2010 to go play politics. And when I returned to Oak Ridge in 2010, I decided I'd rather work on energy-related questions.
So can you discuss how nanotechnology plays a role in your current research?
Sure. Back in 2010, once I returned to Oak Ridge from Washington, D.C., I took over as a group leader in a group at the Center for Nanophase Material Sciences that was focused on catalysis, nanoscale catalysis. And much of what we did in that group was using various nanostructures to control chemical reactions. This was heterogeneous catalysis. We were looking at things like nanoparticle surfaces, or for a while, we were looking at things like the edges of graphene, right? And so graphene, of course, is a pseudometal, and it can donate and accept electrons. And as it turns out, it's a surprisingly good catalyst for certain reactions, like dehydrogenation reactions that we were studying. And in that group, we also had a gentleman who was doing research in nanoscale control of batteries, right? So nanostructured electrodes, in particular lithium sulfur. He was well known for that. And so I started thinking about electrochemistry. How do we use nanotextured surfaces and nanostructures to control electrochemical reactions?
So you mentioned Oak Ridge, and now you're in Los Alamos. Can you share with the listeners the importance of these centers and what their role is?
Yeah, so let's start at the very top, which is what's a user facility? And so it may come as a surprise to most Americans that every big science project in the country, and most in the world these days, this is a model that other countries have taken on, are actually called user facilities, which means anybody can go and do an experiment there if the experiment is scientifically justified. And it usually goes through a peer review proposal process. And it's going to be published in the open literature so that the results are available for everybody. And this goes from radio telescopes to the Hubble. The International Space Station is, in fact, a U.S. user facility, right? Anybody can send an experiment up if it's scientifically justified. And so when we think about things like atom smashers and neutron reactors and the nanoscience centers, of course, we're all available for anybody to come and do science with us if their ideas are good. And so the Department of Energy runs 5 nanoscience centers across the country, which were stood up in response to the National Nanotechnology Initiative. And we're here to serve the international user community. We host the best capabilities in material science anywhere and some of the best talent you'll find anywhere. And we host things like clean rooms where people can do device fabrication for novel solar cells or microfluidics, lab on a chip. Lately, we've gotten into quantum computing, of course, so we're making qubits. and trying to develop, the technologies that will go into a quantum computer. And we do all kinds of things. In fact, we've got a user project right now here at Cint where we're looking at encapsulation of RNA in a bubble for RNA-based vaccine. Yeah, well, who would be interested in that? And as it turns out, there's a fair amount of basic science. I would say these go back to the principles of nanotechnology that go into making those vaccines. And so studying the structure of the lipid bubble itself and how the RNA is encased, believe it or not, we can do all of that at Cint. We have the right capability for that and the people. And so the nanoscience centers are places where university professors and companies and pretty much anybody can come and do experiments, cutting edge scientific experiments in nanoscience that generally we then publish in the open literature. And our users include everybody from Fortune 50 companies to garage startups to professors from pretty much everywhere.
So you mentioned a couple of examples of some of the ongoing work. Can you share other examples or topics that you think are particularly exciting that you've seen be done at these nanocenters?
We have a lot of really exciting work going on. And of course, all 5 nanocenters have kind of a different identity or a different flavor. And so what goes on at one center isn't necessarily what's going on at another. And so CINT, of course, CINT stands for Center for Integrated Nanotechnologies. And so if we focus on the word integrated, what we're talking about there is taking discrete nanostructures, things like particles, rods, thin films, whatever, and assembling those into materials where we can get to technologically relevant dimensions, okay? And what I mean by that is if you want to make a device, whatever it is, a computer chip, a television screen, a prosthetic, you have to actually take something which is maybe on the tens of nanometers in dimension and get it into a material which is big enough to hold in your hand or something like that. And so we call that process integration. And there are lots of ways of doing it. There are self-assembly approaches, there are templating approaches. So kind of either bottom up or top down. And of course, we might use techniques that are available in our clean rooms for this. We might use some fancy chemistry. Other folks around the country do things like use RNA to actually template self-assembly. And so I tend to think that's actually pretty exciting because where we see nanoscience being successful these days has actually been in what I would say is advanced materials, right? Cartoonishly, we might think about nanoscience as nanobots and gray goo, but the reality is where nanoscience has been truly impactful is in developing advanced materials for technological applications. And we're starting to see these show up now, television sets and things like that. But if we look more closely in other technologies that people use on a regular basis, such as microelectronics, batteries, solar cells, these types of things, what we'll see is many of the advances over the last 10 years have actually been driven by advances in nanoscience. And so in a lot of ways, nanoscience is just a different way of looking at traditional material science. But getting back to the concept of integration, what's really exciting here is we're getting to the point now where we're making materials at bulk scale which incorporate lessons from nanotechnology or components and concepts from nanotechnology, which impacts the way that material functions. So if we were just thinking about any polycrystalline material like a metal, we're to the point now where controlling grain size, orientation, boundaries between crystallites, and a lot of the interesting functionality that arises is actually due to these variables, grain size and grain boundaries. And so being able to control these types of things in a material, it can give us really improved performance. And so, we've been able to get down to nanometer device features in microelectronics, largely because we've learned to control materials at that level, right? We have batteries now with extremely high energy and power density and getting safer, largely because we've learned to control anode and cathode structure at the nanoscale, as well as, of course, the separators and things. And so I don't really tend to think about nanotechnology these days as discrete particles and whatnot. I tend to think about aggregated or self-assembled materials as really nanotechnology, because that's where we're going to have our impact, certainly in the near term. Ultimately, if we're going to take advantage of nanoscience and today's technologies, we have to be able to manufacture it, right? We've got to be able to do these things at scale. That's another exciting part of integration, is understanding how to scale nanotechnology to dimensions that are relevant for manufacturing at a cost that's reasonable.
So I want to go back. You mentioned that your user facility is available for researchers to come in and use. And you mentioned companies and garage startups. So if an entrepreneur right now is listening and has a nanotechnology related product they're trying to develop, what steps would they take to use the resources that you have at your facility?
Well, the first step is to give us a call and get in touch with the right scientist here at SIN who can talk to them about our capabilities and where we can have impact. And then, of course, getting access to the facility is a process, and there are a couple of different pathways. If a company is willing to publish in the open literature and wants to study an actual science question, right, that is publishable in a peer-reviewed journal, then of course they can go the traditional user route, which means it doesn't cost anything. It's totally free if they're going to publish the results in the open literature and if their proposal can pass peer review. Not every company wants to go down that path. Interestingly enough, a lot of small companies do like that path because publishing in a peer-reviewed journal gives them credibility. It's instant visibility and credibility for what they're doing. Big companies that want to retain IP control will often do cost recovery type research where they just cut us a check to come in and work. The federal government is obviously cannot subsidize any company directly, at least not in research. And so full cost recovery means they use our capabilities and people and they pay, every dime. And so we have a fair number of folks who do that too. We're happy either way because we just want people to be successful. We want the science to continue to progress. Now, looking outside of the user facility and other avenues that the federal government can support, we have programs like SBIR, for example, and the nanoscience centers participate in SBIR. SBIR, for those who don't know, is, I believe, Small Business Innovative Research or something like that. And it's a program where companies, which tend to be on the smaller side, can ask for a grant to do technology development with the goal of actually having a product for sale at some point. And so the user facilities can participate in SBIR grants as subawardees, where some of the money comes to us to support a garage startup, for example, that might want to come in and use our capabilities to support what they're doing.
And just for our listeners, and we'll make sure that we link in the text as well, this is the DOE Nanoscale Science Research Centers, and they could be found online. There's a portal there. Can you talk a little bit about what types of equipment are available?
At SIN specifically and NSRCs more broadly, we host the best material science capabilities available anywhere. So our clean rooms are on par with anything that can be found at any university. Most of the time, they're much better. There may be just a few exceptions to that, but for your average user, our clean rooms are exceptional. And so we can do full microelectronics patterning from beginning to end. People can come in, we have engineers, we can design CAD structures, do the masks, and then do the lithography. And we can synthesize pretty much any material one could imagine that's nanoscience related, whether it's particles or thin films or various crystals. We don't do, of course, bulk metallurgy, but in terms of chemical synthesis and then physical synthesis methods like pulse laser deposition, physical vapor deposition, and then any number of thin film growths that you'd find in a clean room, such as sputter, E-beam, evaporation, we can do all of that, and we do it very, very well. And then, of course, we all host chemical laboratories where we can do wet synthesis of various nanostructures, particles, rods, graphene, carbon nanotubes. And then we all generally have pretty exceptional capabilities in analytical science. So you'll find the best electron microscopes at the NSRCs, pretty much hands down. Aberration-corrected electron microscopes, sub-angstrom resolution, environmental microscopes, cryogenic microscopes, all of these are available at one place or another. SINT, our specialty is we have a aberration-corrected environmental TEM that can do, for example, gas phase catalysis reactions in situ, and you can see how the reaction is proceeding on the surface of a nanostructure. And we do cryogenic TEM quite well, and that includes full processing under air-free conditions.
That's great. And as director of the coordination office, I would be remiss to not at least mention two things. First of all, I would encourage our listeners to scroll through the past episodes of Stories from the NNI. And we do have some of the center directors from the NSRCs that shared their thoughts. And the NNI user facilities broadly also include the university-based NSF-funded National Nanotechnology Coordinated Infrastructure and the Center for Nanoscale Science and Technology at NIST. So that whole suite of user facilities is really, I think, one of the real gems of the NNI and supports the community very broadly. I want to totally switch gears now and maybe focus less on what's happening at your specific center and your research. And you mentioned that you've been involved in nanotechnology research since the late 90s. What do you think are the most exciting advancements that you have seen in nanotechnology? And then I also want to get your thoughts looking forward. Where do you see some of the most exciting opportunities in the future?
So I've been with nanoscience since soon after they started calling it nanoscience, I think. Although elements of nanoscience clearly go back 70 years or so. Stoner-Wolfar theory, for example. And so I actually feel like nanoscience as a field has evolved quite a bit since we initially started thinking about it. It started out with a lot of interesting promise and exciting ideas, and some of those are bearing fruit, others are not. On the other hand, entirely new avenues or areas have come up that were not expected or anticipated. And so what we're seeing here is this evolution from kind of fantasy to reality. And the reality is very exciting as well, but it's not at all what we thought about initially. And so nanoscience in the 90s was really about, how do we make nanostructures, right? So we spent all of our time thinking about how do we make discrete particles with low polydispersity and control surface chemistry and things like that. And then we started thinking about, okay, well, let's just say we have a nanoparticle, right? Whatever size it is, 10 nanometers. Sitting there by itself, it's interesting physically and chemistry, but technologically, it's not interesting because what do you do with a little nanoparticle sitting there, right? And then we started thinking about, okay, now that we can make these nanostructures, how do we incorporate them into materials so that we can actually do something interesting with them? And then we started thinking about interfacial chemistry, and then, of course, all of the emergent properties that can show up when nanostructures start talking to each other in a complex material. And so the science got more and more complex and interesting. And now we're to the point where we don't think much about how to make discrete nanostructures. We think about what are we doing with them. And let's just take graphene as an example. For a long time, graphene's a really interesting material, had a lot of promise, still does, but graphene initially has all kinds of interesting physics that when it was first studied, we started thinking about, wow, you can do all these things with graphene. Maybe we can make advanced electronics, maybe we can do this and that. And so we spent a lot of time figuring out how to make high quality graphene in large amounts. Then we started thinking about, okay, how do we pattern graphene and get it into a circuit, right? And we've gotten pretty good at that as well. And now we see, well, you know what, graphene by itself is interesting, but what if I stack it with another 2D material? Now I can start getting emergent properties. And so now we're thinking about sort of composites, like single atom composites, where we might stack a 2D chalcogeny with graphene or various different chalcogenides. We can stack them at different angles. We can get interesting interference patterns and very interesting electronic structures. And so what you see is a progression from very simple how to make a basic material and study its physics, all the way up to how do we incorporate it now into something even more complex. And this is where we are actually, right? In the last few years, studying stacked 2D materials now has sort of become the hot topic for 2D materials because there are additional degrees of freedom. Of course, the NSRCs are all very good at taking these stacked materials and then sending them through the lithographic process and making devices. And that's what we're doing, and that's what our users are doing. So what's exciting is now we're getting to the point where we're less focused on fundamental synthesis and we're more focused on how to apply what we've learned into actually solving problems. And that's exciting because now we can draw a straight line from our work to solving problems outside of our laboratories, which ultimately is sort of what the public expects of us, right? We're here because the public understands, going back to World War II, that funding basic science results in more rapid progression of technology and a better quality of living. So now we're getting to the point where we can take what we're doing and we can improve things outside of the laboratory. And to me, that's probably the most exciting thing is actually impact. And I don't mean impact in terms of a science paper, I mean impact in terms of solving a problem.
So you have this experience looking across the nanotechnology landscape, and you've been working in this area for some time. I imagine that you have the opportunity to work with people from a lot of backgrounds when they come in and use your user facility. What advice do you have for students that might be interested in pursuing a career in this area?
If I had to go back and tell myself what to do in the early 90s when I was an undergraduate, I would say actually chemistry is great, but study more math, because what's happened in science is the contributions of theory and high performance computing has just been enormous, and it's growing faster and faster every year. And so at this point, the very best science is a tendency to be a collaboration between the experimentalists and the theorists. And the reason for this is, and this is especially true with nanoscience, there are size and time scales that cannot be probed experimentally. I studied a fair amount of math, but at this point, scientists who's thinking about going into basic materials needs to definitely keep one eye on maybe even taking some classes in order to better understand what goes on with theory, because it's frankly such an important contributor to what we're doing.
Study more math. I think that's great advice. So thank you so much for being with us today. Do you have any closing thoughts that you'd like to share?
The model of user facilities is a wonderful one. It's a great way for the federal government to push technology forward in a way that doesn't pick winners and losers. The government simply subsidizes a capability to be out there for anybody to use if they choose and want to pay for it or want to publish it in the open literature. So it's a really good model, which is why the rest of the world has picked up on it.